with an amazing challenge owner. And he then hired us for 3 years to monitor regenerative agriculture and for illegal logging, etc. in Indonesia. So I do want to tell you this because Indo Data Week also has a hackathon. So, you know, this is the ideal case of what can happen in a hackathon. But yeah, it's also a cool fact of Space4Good. We do open innovation projects as Space4Good, also technical work between GIS and remote sensing. And that is what we'll be telling you more about later. Now, Fede, on to you.
Yes, thank you. Thank you for inviting us. I'm Federico, originally Italian. I have my background in environmental science, but then I decided to specialize my knowledge and my academic career through the satellites observation, Earth observation, and GIS. So now I work as a GIS and remote sensing specialist at Space4Good. With the passion of innovation as well, but trying to merge as well the AI technology with the satellite imagery and Earth observation to give good insights on what is happening and how to manage better resources. So super excited to start. I can share my screen already, right? And then let's roll up.
Perfect.
I think Parvati has to accept my yes.
No, you can share, I think.
You should be able to see my screen, right?
Yes.
Yes.
Great. I want to start from this quotation from the British physicist Fred Hoyle, which say, once a photographer will be taken on Earth outside, a new idea as powerful as any in history will be let loose. And I want to start from this concept to talk about a little bit of history. From millennia, human being could only imagine what the Earth might look like seen from space. And some ancient Greek philosophers had suspected that the Earth was probably a sphere, right? But where was the visual evidence? From the late 18th centuries, hot air balloons first saw the Earth from a new perspective. There was not part of the Earth itself, not from the top of a mountain or from the top of a cathedral spire. To see more of the Earth's curving horizon, clearly a higher point of view would be required. To rise higher would be required not a hot balloon, not a plane, but a rocket. In the morning of Christmas Eve in 1968, one of the astronauts aboard the Apollo 8 spacecraft, Bill Anders, turned the camera from the supposed objective of their mission, which was the moon, toward a spherical, brightly glowing and blue object rising above the lunar horizon. That was Earth, our irreplaceable planetary home. Suddenly, humankind was able to view its own habitat, in an all new way, with an all new perspective. And it suddenly emerged that for it what really was. So it was just another medium-sized planet in another solar system, in one galaxy, in an infinite universe. Well, from that moment, when perhaps the most famous photograph was ever taken, until now, just 50 years have passed. And today, we hope to give you an introduction of a huge range of possibilities and technologies which allow us to look at our Earth system in a more comprehensive way. So with this, I want to give you the official welcome to our GIS and remote sensing workshop, Traps, Illusions, and Tricks. And still a big thanks for Indodata for having us here as a Space for Good. This is the agenda. We put some time framing over here just to as a reference. Then I will pass the screen to Elke. But yeah, we thought about a GIS introduction, and an exercise on GIS operations, a little break, other introduction on remote sensing specifically, and then another exercise on remote sensing. I hope you enjoy the journey, and I give the floor to Elke.
Thanks, Philip. Yeah, great start by looking at the blue marble. I'm gonna take over now. So just let me know when you see this. Are you seeing it correctly? Yep.
Yes.
All right. This. Okay, so we first start with GIS. As Pele was saying, we're passionate about studying the Earth, and of course, GIS is derived from the older profession of cartography. So here we have, some visualizations of old maps, how they interpreted, especially how the Americas were. And I'm gonna, as the name of this workshop, we didn't want to do flat out GIS. We wanted to give you some spark, some tricks, some illusions. I will first start by telling you a story. And it's a story of something that's called paper towns. And this is also in connection with the old profession for cartographers. What they used to do is that they used to draw a fake town or a fake street, and drawing this in a map, only they would know that it was there. And it was kind of a copyright trap, such that if the map was copied by someone else, they would know that it's a copy, right? But this is an interesting thing of what happens with reality then, because this town, Aglo, was drawn on a map, it was a paper town, then people started stopping there, and then it had a store, so it's actually something that was not there and then became reality. So I thought it was a funny story from the mapping world, and a good way to start. We'll be sharing some of these funny stories, tricks throughout the presentation. So next slide. Just wanted to give you a quick impression on some projects or project types that we work within Space4Good. The first one, we did a rooftop analysis of Rotterdam city, and the second one, we can use, we can do land use classification via GIS to determine what is agriculture, what is building, what is forests. So with the tools that you learn today, you'll be able to do such projects. Of course, more study is needed. This is just a brush through, but it'll set you on your way. And then I come to the question of why spatial and geo. And here the quote: if the Facebook is the who and Google is the what, then Esri is the where. I'll be talking about Esri. Esri is one of the most, actually pioneering companies in the GIS spectrum with their software ArcGIS, ArcMap. And this is the founder, Jack Dangermond. So I want to kind of put you in the puzzle of who is who within this world. And then this is a really awesome professor, Carl Steinitz from Harvard, and he created something called the Framework for Geodesign. What I really like is that his thesis is there is design professions such as civil engineering, architecture. They really focus on the house, and that's it. And there's the geographic sciences, which focus on meteorology, atmospheric sciences, etc. But there's few things that bridge this gap. that put them together. How is this house embedded within the river system or the watershed ecosystem? And this framework of geodesign puts it together. So I highly recommend studying this. So this is just extra tip. As I mentioned, Esri is the commercial counterpart of GIS, but there's also the open source, which we're a fan of, QGIS, and this is the software we will be exploring today. Now, one of the most basic but most powerful elements from GIS is that you can do an overlay of several layers. You can have images, you can have a land cover map, demographics, wetlands or watersheds topography, and overlay them all based on the same what we call coordinate reference system. Let's say they can all merge together in the same space, and you can actually see very informative visualizations. I love visual. I need to see things and also colors. So it takes new meaning when you can put all the layers on top and just see the interactions between these layers. So it's a basic operation. It's just getting your layers together and finding the proper coordinate reference system to put them in. But once you do, you can find already insights with this. The second thing is that we have different layer types to work with in GIS. We have vectors, which are like more physical, more object type, and raster, which are more based on the image type of formats, which are based on pixels. If you see the vectors, we have line file types, we have point file types, and we have polygon file types. We'll be exploring with these in the exercise. Now, I was saying about coordinate reference systems. This is actually one of the most powerful things about GIS. We have geographic and projected coordinate reference systems. Each layer has to be associated, and depending for the use, you choose which one to select. So, what's a geographic coordinate system? Well, this is when you treat the Earth in its round format, in more its round, its 3D shape, right? But the Earth is actually it's actually more looking like the red line here. It has mountains and valleys, etc. But we have to approximate this with a mathematical model, which are mainly ellipsoids. So if you have a Earth-centered ellipsoid or datum, you find a good fit overall across the Earth. But if you want to have good detail in a specific place, you might find one that it fits well, matches well to the specific place you're interested. So I put this example, specific names, WGS84 is the ellipsoid, most popular ellipsoid used for the Earth. This is actually what uses Google Maps. But then in specific places, you have others. In the Netherlands, we use Amersfoort. And I'm not expert with India data, but I think one of them is this one in the case of India. These are the codes that you can use for searching them. So this is talking about more the 3D Earth. But we talk about projected coordinate system more when we talk about cartography, about the maps, how we translate these into 2D, into flat paper. So depending on the use, if you just are using, for instance, Google Maps, let's say, you don't need to have a projected coordinate system. But if you need to turn in a set of blueprints for a municipality, you have to use the projected coordinate system. This will give you the proper distance relationships, etc. Then finally, I go to operations. There's lots and lots of operations you can do with GIS. There's actually toolboxes, both for vector operations and for raster operations. Yeah, here are some of the types. You can do location analysis, terrain analysis, distribution, neighborhood, spatial analysis. These all don't make much sense. That's why we do an exercise to see how they function. I'm gonna specify on some of them, which are actually some of the most common but also useful operations. So in the vector set, we have buffer, which is taking one of the three vector types, either a point, line, or polygon, and create an extension out of this point with a certain distance. So like a radius in this case, or just a 15-meter extension along the line. And then clip, it's like taking a cookie cutter. You have one layer and you put a cookie cutter and you get this output. So these are two types. And then in the raster set, we have map algebra, which, if you remember us talking about, this is more a layer which is more based on pixel. So in this case, each pixel has a value. And if you sum, for example, this layer plus this layer, you get this output, which in this case 5 would have the higher rating. This is really really powerful for doing suitability analysis. So you could take a layer saying distance from a road. So you'll have a different pixel values for the distance of the road, and then, for instance, it can be another distance to the center of the town, and with these different scores based on these pixels, you sum them together and get this area as the best place to choose it for something, for construction or something. And then another operation called cost path. I'm gonna stop there. I want to ask if there are questions up till now for the participants. Otherwise, Fede is gonna take over and use QGIS to explain all this that I said quickly in words. But first, are there any questions by you?
Hi, really thanks for the presentation. I have a question. Can you hear me?
Yes, we can hear you.
Yes. So I had a question about the raster image that you showed. Is it similar to an adjacency matrix? Or would you say it is it is completely different?
Adjacency matrix. I'm sorry, I don't know that term. Fede, do you know this?
So I can give a bit of context. So it's if you look at network science, that is something that you use for the shortest path problem, right? Is to so maybe it is completely different than if you're not familiar with the term.
Maybe what we can do, Fede is gonna show later on some example of raster. But let's say, like, even a satellite image is considered a raster. So it's anything that's based on pixels, but you can also derive your own raster sets. So if you see, let me take over again. If you see, one moment. Oh, if you see this image, you see how here we have the real, not the real object. We have an object version of a river, for example. But if we convert it into a raster, you can actually do that. You can convert between vector to raster. How this will turn out is these pixels, whatever pixels touch this line will get colored as blue, or a pixel value that represents a river. So this is actually how a raster, if we convert from vector to raster, it'll be this. In the case of point, we have just this pixel colored, and you can do, yeah, same with the polygons.
And then the polygons, the raster image that you show, that is really dependent on the resolution really depends on what is the size of that single pixel, right?
Correct.
Because
Absolutely, yes.
Yeah, okay. So it will completely depend on the aggregation that you take. It's 1 kilometer or is it, okay, great.
Yeah, so you can set this resolution also when converting. Some resolutions, of course, come fixed. You know, like if I embed a satellite image, it's a raster, but it's kind of the resolution is already given by the satellite image. But if you're manipulating, for example, if you're converting from this vector to this raster, you can indeed set the resolution of those pixels. So yeah, more finer resolution will give you, you know, yeah, I guess it will not be as coarse. This image shows it a little bit coarse. Does that clarify?
Yeah, thank you.
Or any other questions by participants?
Yes, there was a question about the data that we sent. Please.
We can go.
Yes.
Yeah, there is a question, or we can
make sure to unzip the file, the folder, and we will use that data within the QGIS environment. So do not worry if you didn't have time to do so. We will send after the workshop a file where you can follow step by step the tutorial again. So I hope you can follow me now, but there's chance to do by yourself as well later on.
And also, yeah, I think for the sake of just maintaining the time, you know, like try to pay attention and follow along. But otherwise, there's the recording of this workshop and also the manual that's prepared by Feli. So yeah, Feli, on to you.
Yes, I can share my screen again, and we were here. Yeah, let's exercise QGIS. And why QGIS? It's already been said, it's an open source tool. But why QGIS at this Indo Data Week? We decided to go for the first exercise with a specific SDG goal, SDG of the many ones, which is number 6. Number 6, which is ensure availability and sustainable management of water and sanitation for all. So let's talk about water through this exercise.
We're not seeing your presentation. We're seeing
presentation. Yeah, that's fine because we will start from using QGIS directly then. Okay. You can see my screen on QGIS environment, right?
Yes.
Okay.
I can see the platform.
Great. So for whom is not familiar with the platform, if you can just open the desktop version, you might probably have already downloaded, and many programs came with along with the setup. But we will use today the desktop version. And if you just open the program, you will have this first window. We can create a new empty project. And we will go a little bit through what is the platform about. So we can find many tabs here with specific operational tools. And as mentioned by Elka, there are the two different tools for the two different type of data we will work on today. So vectors and raster. to create new data or to open new data. Obviously, there are many folders here, many tabs here, and is the window of the layers. So the image that Elke was showing before, how we can put upon another one the different layers for the same specific space location. This where in this window all this layer will pop up. Then we have a tab to open here this window about the browser. So many data can be accessed by links, for example, or by services that are already online, and we can import them in our specific environment. Instead, as you can imagine, this big window here is where the map will be shown. So where we'll actually see the map. Let's start with the first exercise and a little introduction. Let's put a task to solve for this exercise. What is the task of today? Is find a suitable area for installing a new water pump between two cities in India, Teni and Kumbong. I hope I'm saying them in a right pronunciation, in the Teni district. Let's say that someone give us this work, and we have to manage how to solve this task. And there are some requirements to solve this task. The new water pump has to be installed a maximum 25 kilometers from the city of Teni, maximum 15 kilometers from the city of Kumbum, and maximum 500 meters from the water stream. So there has to be a water stream, and a place between the two cities can be suitable to install this water pump. So let's start with data. We sent you a folder where there are mainly 3 subfolders: rasters, vectors, and text. So these vectors and raster are the 2 types of data we've been talking about. And let's start opening on the folder vectors, the file some Indian districts. I just use some in the south region because of it was too heavy. So we have some districts as a vector files in a vector folder, and as you can see, for each specific file, vector files, we have different formats. The one that we will use is SHP, so it's the shapefile format. We just drag and drop in this layer window. So as you saw, once we drop it here, we immediately are able to display the some Indian districts in our map. You can click on your right button of the mouse, so right click, and you can open attribute table. What is the attribute table? It basically tells us the information that are inside within this specific layer. As you can see here, this specific layer of this some of the Indian districts there are 91 features. So each feature is displayed in one row, and for one specific region feature we have different properties. So we have the district name, we have some codes that can be referred to understand which region or which district we are talking about. I've been saying so, we can explore different type of information. Double click and you can change the style of the layer if we want to display it orange instead of pink. But we can even have extra information on the coordinate system, of the type of file that we're talking about, how many features are contained, and so on and so forth. Okay, once we have we have our some Indian districts on our layer window, we can query now a specific region, a specific district, because as the task was saying, we need to find a suitable area which is contained within the Theni district. So we can open the attribute table as we did before. So open attribute table, and we want to query this data. What is the way to query this data is to select features using an expression. So we click on here, and there's gonna be this tab that will allow us to query the specific fields that we need. How we do so? Here there is an expression. We can look for here fields and values. I can put this a little bit bigger. And we can say the districts, double click on district, look for all the unique values and search for the Theni district. We found it here, so we can say district equal to Theni. We can select the feature once the expression is done. And in our attribute table, we will see suddenly that one feature was selected, which is obviously the Theni one. And as you can see on the map, our selected feature is highlighted in yellow. Okay, now we want to save just this specific district. We don't need the other one. So how do we do so? We right click on the layer and we export as a save selected feature as. So we are just saving a new vector file which contains just the selected feature. As a S3 strip file format, we decide the location where to save this vector. Obviously, to have a tidy data, we will save it in the vector folder. And let's say that we want to call it Theni district. So we're saving just this specific district. Let's save it. Okay. And now we can play around with visualization here, switch off, switch on the layers. We don't need all these different districts. And we have here just the Theni district. Well, once we have this, we can add extra layers. We want, for solving this task, we need to know where the CDRs, where the water stream are, and calculate the correct suitable distance between them. Let's add the streams. So let's go into our folder, always vectors files, and you will find water streams file. Always the SHP can be drag and drop in our window, and now we can see all the streams that are around the area. Let's start now to do the first operation of this exercise. We want to clip, as was mentioned before by Elka, clip just the streams that are within this boundary, the Theni district. So we don't need these streams over here. How do we do so? These are our vectors, so vector tabs, geoprocessing tool, clip. What we add as an input layer are the water streams overlay layer, that is the Theni district. We can save it as a temporary file for the moment, but it's saved into file as well. And how we want to call them, it's water streams, specifically for Theni. Let's save it and run. Well, if we switch off now the water streams that are there for the entire area, we'll see that what we gain now is the water stream that are just within the boundaries of any district. As for this specific layer, we can even change visualization. Let's say that we want the Teni district to be just highlighted as a borders. So if we change the symbology here, we say that we don't want any filling colors. We want a solid color in red as borders. I did this operation quite fast, I understand, but if you're not familiar with QGIS, but just playing around a little bit, it's super easy and user-friendly. So these are the borders, and let's say that we want the water streams in blue to have a better visualization. Great, so borders of the Teni district and water streams. What we need now are the two cities, the locations of the two cities. Well, for the specific city of the Kumbum city, we want to use the text file because we've been talking about rasters and vectors files, but there is even another way to insert data in a geospatial environment, which is through text. In fact, if you check your folder, there are three subfolders: rasters, vectors, and text. If you open the subfolder text, Kumbum city, you will find a notepad which says basically three informations: the name of the city, the longitude, and the latitude. These are information that are basically not spatial in this moment, but in a text file. We want to import this file and make it spatial. Let's put it simple. Okay, how do we do so? We can click here on the data source management, and when we can import the specific data, which was in the text subfolder, Kumbum city. We set parameters for longitude as an X field, latitude, and the coordinate system, which is now UGS 84. I will wait just 1 minute extra to make sure that who is doing the exercise has the same parameters here. Once this is done, basically you can see already the sample data. What we saw here in our text, in our note down here, presented on QGIS. Once you insert this specific parameters, we can add the layer on the map, and suddenly you have here a point. So a point feature that is a representative for the city of Kumbum. Okay, we need now the other city. We need Teni. We will add in a more a common way, which is basically a vector file already here that I prepared. Teni district and Teni city in the vector subfolder. Always the shape file. We just drag and drop, and we have it here. So as you can see now, we have all the features that we actually need. We have the borders of the Teni district. We will have the two cities, the city of Teni and the city of Kumbum. And we have the stream, the water streams of the area. We can even inquire this data if we are not sure which city is what, with, for example, this button here, so information. So if you click on Teni city, it will display that this is actually the what we're looking for, Teni. We're not selecting any feature here, we're just inquiring the data. So just select and see what the data are. Okay, how we solve the task? How we understand what is the best just join us. The new water pump has to be installed 25 kilometers maximum from the city of Teni, 15 kilometers from the city of Kumbum, and maximum 500 meters from the water stream. It has to be some, we know we can assume there has to be somewhere over here, right? The two cities are here, somewhere in the middle, I don't know where. But let's do it this geographically. And how we do so? We can create buffers. Is the other operation we were talking about? And the first buffer that we create is about 5 meters buffer from the river. How we do so? Vector, geoprocessing tools, buffer.
I don't know, sorry, if it's a good point to ask if there are questions up till now before you enter into the buffer operation.
Yes, because I'm not seeing the screen from the chat, so it's smart if you can tell me already if there is any.
No, there were questions on downloading the data. So yeah, any one of you that haven't got it, please send me an email and I'll reshare the link. For the moment, I would suggest just follow along and then with the recording, follow it by yourself calmly. But are there any questions in relation to the file types or the operations that we have discussed so far? So the first question is, you first performed the clip operation. That's a good question. Actually, it was not a clip. We just selected the district and then just resaved it as a new file. But if you know, it could have been done also with a clip. You're right in the fact that it could be another approach, but these districts are already delimited, so you just have to select it from the original file. I hope that answers your question, Ravi. And then, yes, you'll be able to watch the replay because this is being recorded.
Yeah, let's say that for the same task, we can have different approaches. This is just one approach, how to gather the data, how to arrive to certain suitability maps. There are different operations that allows you to work with data. It's the most important thing, I would say, is just analyzing first the data to see what is already available. We have already here all the districts, so yeah, it doesn't make a lot of sense then to clip this towards that one. It's more, yeah, it's more efficient just to decide to select a specific district and save it as a new layer. But then, yeah, there was a clip involved that was basically from water streams that was comprehensive of the area. We just selected and clipped. We just clipped the ones that were within the boundaries. Can I go ahead, Elka? There are any other questions?
Yeah, go ahead. Yeah, more for the time.
Yeah, great. Cool. Now, okay, we want to make a buffer. We were in a stage of making a buffer around the two cities and around the water stream. Let's make it first for 500 meters from the water streams. So vector, geoprocessing tools, buffer. In here, the input layer has to be the water stream of Teni. The distance has to be 500 meters. This is basically a requirement that we have from our commissioner. We run the operation, close it, and as you can see, this is the first example of buffer. So these are the water stream, and in green you see the buffer area. We can even check this 500 meters if you want. There is here a tool which is basically a ruler. You can go click on it. Yeah, and see the 500 meters. Obviously, it's not precise because it's depends on where you put your mouse. Great. We have the first buffer now. We can save it again if we need it, or because in our case, when you see this little icon here, it means that this is a temporary layer, so it's not saved yet. It's just up to you if you want to save it or not, but we can even rename it here. Rename the layer and say this is the TENI. Let's start again. Water streams TENI 500 meters buffer. I'm not doing this casually, like adding all the names of what we do in each layer. It's just how to track better the data. So if I want to go back or give this data to someone else, it will soon understood that this is a buffer. It is not the water stream itself. Okay, we have to do the same operation for the two cities. We will make just for one, and then the other one will upload it to make a little bit the process faster. We'll make it for the TENI city. We said that we have to make a buffer of 25 kilometers. So again, let's repeat the same operation. Vector geopressing tool buffer for the TENI city. Instead of 5 meters, this time we want 25, and we can change here the scale. So kilometers, 25 kilometers. Let's run it, close. And this is the buffer of 25 kilometers around the city of TENI. Well, as I said before, we can just go into our vector folders, and there is already a Kumbum city 15 kilometers that I prepared for you. We can drag and drop here. We can rename the buffer of TENI to make it consistent and say TENI city 25 kilometer buffer. Great. Now we have all we need. We have the areas that is 25 kilometers in the span from the city of TENI, the one from the city of Kumbum, and we have the buffer around these water streams. What we need to do now is to interpolate this data, and how we do, we use another operation, which is intersection. We first intersect the two buffers of the cities. So the input layer is city of TENI and the city of Kumbum, the two respective buffers. We run it. And the result is this specific area, which is the result of the intersection of these two buffers. We can rename it, right click, rename as a intersection cities between the two cities. But this is not enough. We have to still understand which one is the most suitable area, which is within the two cities and within the 5 meter span from the river stream. So we make another intersection vector, geoprocessing tool, intersection. And this time we intersect the cities with the buffer of the water stream, which is exactly this one. Let's run operation, and this is our resulting area. So to recap, our task was to find suitable area to installing a new water pump between the two cities, and the requirements were being maximum 25 kilometers from the city of Teni, 15 kilometers for the city of Kumbum, and 500 meters from the water stream available. And these are the two suitable areas where, according to our requirements, we can install a new water pump. I'm exactly on time, 25 minutes that I was supposed to be dedicated on this exercise. Please, if you have further questions, don't hesitate to contact us. It's right in the chat. But as I said before, who wasn't able to follow exactly this exercise, we'll send later on a step-by-step document where you can go through and work with data and with your different operations. I will stop sharing my screen. And the floor is yours, Salka.
There was a question sent by email saying that QGIS was not being able to open. I'm not so familiar with the folder you sent. Could you explain a little bit, like they have to open the desktop, or I don't know, any other tip?
Yeah, there was in the folder that I sent you, there is a README file too. So you can go through that, and it's a setup for, I think, normally Windows, but it works as well on iMac, on Macs. If that links for you doesn't work, you can just go on the QGIS portal and install the specific setup for you. But in general, it should work for the most. Once you click on the setup, you will many programs will be installed, all related on QGIS. But the one that we have to use for this specific exercise is QGIS Desktop. Yeah, I don't know if I answered the question, but probably there are other questions as well related to files. Okay, are there any feature or rows of data? For this kind of data, for the vector files, each rows contain a feature. So it's a specific point, specific line, or a specific polygon. We don't have an attribute table, for example, for raster files. We'll be able to watch replay. Yes, sorry, when to use vectors, rasters, and text file. Well, this is a good question. This is not really up to us in the sense that obviously we can always make operations like vectorize or rasterize data if we need accordingly. But most of the time is even what is out there, right? So for this kind of data, it's quite hard that it happens that we go on field to collect them, even if I have to say that it's possible. I did some project where I had to go with a GPS and go around and collect points and then work with that. But for satellite data, we have rasters. Most of the time for a database, like institutional database, we have text files. So we have Excel files, just coordinates, just numbers as usually are represented, and then it's up to us to make it special to in our QGIS environment. It's quite important to collect requirements for each analysis. It's yes for sure. It's the suitability map. It's always take into account different requirements. And some requirements can come from the client itself. So the client has different questions and say, yeah, I want to install this, so I want to have this specific analysis. Sometimes these requirements come from the nature of the data itself. For example, if we know we want to work with data that are with wildlife and animals, and we know that the habitat of a specific animal is span 5 kilometers from a river, then is something that you know, and there is no a client that tells you that's requirements. But obviously, for each project, having specific requirements is really important. There is the last question I can answer, and then I can give it to you. Is it possible to do optimization with QGIS while introducing constraints? Yes, it's possible. I have to say that QGIS in our industry, it's a really great tool to use because it's open source. There is the most important thing is that it's a community behind that. So there are a lot of people that are willing to help, a lot of video tutorials, a lot of step-by-step operational things. So it's obviously all this to consider when to use a tool. But it's possible to do obvious optimization and even to contribute on to program something, because it's obviously open source, so you can even contribute with a new tool or a new operational, a new workflow.
I think on this of the constraints, it also can depend on how you view things, because you know, if you take, for instance, a lightning, like the high voltage lines, for example, you can have a design constraint that your project, for example, your construction project should not be within 20 meters buffer of that high voltage line, so that you can introduce as a constraint, and the buffer, you know, in this case would represent such limitation or such prohibition. All right, I think that we hope we answered the questions. Due to time, we're just gonna, I'm gonna share my screen again, but we're actually gonna take a 5-minute break just so that, or you can refresh yourselves and come back for the remote sensing part. Again, they're both, you know, high-level brush through topics. I will say that we have listed some data sources where you can find data. I need to improve links for India, but this was, the first one was actually shared by a colleague that we have from India, and we were also talking by the creators of this India Urban Data Exchange, and there are some other for accessing world data. So with this, we put for the break, we put this video. Just go grab a glass of water, and we come back. Let's say at 5:08, and we start with the next part. Okay. Sorry, not fat. I'm using my clock. Just take 5 minutes from now, and we come back. Okay.
Yes. Okay. Thank you.
All right, everyone. I hope you stretched your legs. And I hope most of you are back. We have 35 participants. As we said at the beginning, this second part of the presentation will be talking about remote sensing. And we'll be telling you why optical illusions, but that's part of our tricks, illusions, and traps subject of the workshop. Are most of you back there? Let me, oh, hello? Is everyone still seeing me, hearing me?
Yes, we can.
Okay. I'll share my screen again, and I'll go ahead and start. Hopefully you're there. So, as I said, remote sensing and optical illusions. Here we have some of such optical illusions, and you might be wondering what is the connection between these two subjects. We'll tell you throughout, as we said. Mainly we'll be answering this question on, are our eyes reliable? Okay, so I'm not gonna say the answers now. I just want to leave you with this hook, because we will actually be exploring this in the duration of this talk. Same as with the GIS part, I'm first gonna start talking about what are the potential analyses you can do with remote sensing data. Well, in Space4Good, these are two projects we have done. You can take data to perform satellite data to perform biomass estimates. So this can be related to agriculture or forestry. And a lot of the remote sensing applications are actually done in these two fields. We need more in the marine sector, but we also put this project on NO2 because we also have a new satellite called Sentinel-5P, relatively new, and it takes data on the pollutants on the air, and as such we can monitor for example, NO2 across countries or cities. And this was quite important for the COVID. I don't know if you saw, but the cities that were under lockdowns had less cars, less transportation, less industrial activity, and as such, the NO2 reduced in the lockdown months. So this is some of the analysis you can do. I first start with more theory on what is remote sensing. We introduced this in this talk also because more and more, there's more remote sensing data available, and there's also much more operations and analysis you can do if you complement both GIS and remote sensing together. So even though you might not be particularly interested now on this, you might come across it along your geo journey, and we just wanted to give you a brush stroke through it. So I first put a video on what is remote sensing. I'll put just 1 minute.
Remote sensing is observing a medium, a process, some phenomenon without ever coming in direct contact with that phenomenon. So unlike a lab experiment or where you go to a place and make an in situ measurement or actually touching the medium, remote sensing is observing it remotely from a distance. And this actually provides a different kind of perspective on things. When you're part of your medium, you're part of your experiment, you're part of the experience, you get one perspective that's crucial. You get a very different one when you're removed from it, when you're looking from space, when you're looking from 400 or 500 miles away, or in some cases 20,000 miles away. We can start up close, we can stand in a place and look at it, and we can zoom out, and all of a sudden it takes on new meaning. The trees are part of a broader system that sit on a landmass that is a country, that's part of a continent, that sits in an ocean. And as we step back further and further and look at those same trees, we may not see the leaves from far away, but we see the trees and how they fit into a broader Earth system, the clouds that surround them, the ice that's far north or far south of them, the oceans.
All right, I stop there. You get the idea. I want to contrast this definition about detracting yourself with this statement of the overview effect. This is when the astronauts look down on Earth and they have the chance to appreciate our home in its entirety and reflect on its beauty and its fragility at once. So this is actually a statement from the Instagram account Daily Overview. They take remarkable pictures using different satellites and drones, everything. They enhance them. We'll be showing some pictures by them. They're more close to art. So yeah, this is, it's both art and science, what we're talking about now. The first slide I want to show you is that in this detraction, in this studying your medium from a distance, there's different methods. It's not just satellites, we typically think of them, but there's aerial photography, drones, space shuttles, and airborne radar, for instance, which can all be instruments to study the Earth from a distance. In terms of satellites, we also have tons of different types of satellites. We have military satellites, scientific, communications for TV and radio, weather and navigational satellites for the GPS. And our particular interest in this field is the Earth observation satellites, which study land, vegetation, and water. Another categorization is that we have both commercial and non-commercial satellites. The non-commercial were typically put out by governments, were very big satellites, and they still have them operational, but now we've seen a rise in a lot of commercial initiatives, and they are of course pricier, but also the size of them gets much reduced in some cases. And then this next impression is, well, just an idea of how many of these objects are up in space. It's you know, it's close to our traffic in the Earth system. It's just there, it's quite a lot. So as of 2019, there were around 5,000 satellites, only 2,000 operational. This website also gives you an impression. One moment. Of the different satellite elements. Again, not all of them are operational, but I like it because you can also see the orbits, the paths that the satellite takes. So you can explore with this. So this is just a overall introduction to put you in the field of remote sensing. Now we'll be talking about how to find your data. What are the parameters that you can use to actually get the data you need? So for this, we talk about 3 parameters or 3 resolutions. We have the spatial, temporal, and spectral resolution. I start with the spatial resolution. This is the size of 1 pixel on the ground. So if you have lower spatial resolution, as you can see from this image, it's more blurry. It's not as crisp. When you have higher resolution, the pixels are better. You can see the almost the boats, the buildings, and perhaps even individual trees if you get higher resolutions. These are pictures from the daily overview account using NearMap. This is of 5.8 centimeter. Here you can see the cars, the containers, and you can contrast this with one of 15-meter resolution by one of the NASA satellites. But both quite pretty. Now the second parameter, temporal resolution. This is the revisit time, or the time for one satellite to complete one entire orbit cycle. And this is important because what this gives us is actually the days between images that you get for one same spot on Earth. So Sentinel-2 is a popular satellite we'll be discussing throughout. There's 5 days between images in the same spot on Earth. And this is important, especially due to clouds. If you have clouds, if you're in a tropical area, it might make sense to look at images with higher temporal resolution, with like 1 day frequency between images, because the chances of having the spot without clouds will be greater if you have it at 1 day frequency. So this is just a graph showing these 2 parameters, how you can interplay between both of them. It's not always that higher spatial resolution and higher temporal resolution is the best. Having both of them in its highest form means more data that you need to process and store and potentially pay for. So it's not always, and if you need to do a countrywide analysis, you don't need such centimeter resolution or 1 meter resolution. You can do with something around 10-meter resolution and revisit time of weekly or 5 days. So this is just to orient you, and again, mainly to say not always the highest of both is the answer. You actually end up with the other problem of too much big data. And then the third parameter is the spectral resolution. And this is actually what we talk more is the more deeper remote sensing analysis, is where you understand the back end of how remote sensing works. And I first start with the fact that our eyesight is a form of remote sensing. If you look at the electromagnetic spectrum, the blue part is the only part we can detect with our eyes. So it's quite a small fraction, right? It's the visible part of the EM spectrum. So with remote sensing instruments, what we do, it's actually an extension of this visual field. So we have more access to information about the physical world. So again, the eyesight is just this part, gives you this part of the electromagnetic spectrum. With satellites, you can look at gamma rays, infrared, radio waves. So it's just, you get more breadth of access to data. Then we talk, now we zoom in into the passive satellites. These are the ones that we will be studying now. They detect the sun radiation that is reflected from the Earth. So the sun emits radiation, it bounces back on the Earth, and this gets recorded by a satellite. And these are called the passive satellites. You have also active satellites, which are more radar, and it's radio waves that are being recorded and transmitted. So in the case of the passive, the sun, the solar radiation bounces on the different materials on Earth, and they all reflect and absorb light differently. And that's actually what we're measuring with remote sensing, these different reflections and absorptions of light. So what we do with remote sensing is we actually detect and record the EM spectrum and how the different materials bounce it off. So in the case of the passive sensors, we work in this section of the EM spectrum. And in the case of resolution, if we record the EM spectrum in different places, if we record it in few places, we have low spectral resolution. If we record it in many places, we have higher spectral resolution. So what we call this is the number of bands. These are the number of places where we record it. So if we take, for example, a normal camera gives you 3 recordings of the electromagnetic spectrum, the red, green, and blue. But with remote sensing, you have more access to more places within the EM spectrum, and thus you get much more images, much more bands, let's say. So with Earth observation, the satellites we'll be talking about here, we focus on the multispectral. And if you can see, the Sentinel-2 is the one I'm referring to. This records the EM spectrum in 12 places or 12 bands. But you can have up to 36 bands. The hyperspectral are recording it in more than 100 places, okay? So I now come back to the question of, are our eyes reliable? And you'll understand how and why this tags in. So the first part is that, as I mentioned before, we have a limited view on the EM spectrum, so remote sensing instruments expand this. But then it also happens that in the case of the optical illusions, two things can happen. Either the visual system is tricked, or the brain, so the neurological system, fills in gaps for you. So I next go to show you this video and ask you this question: is the square changing the color? Let me play it again. So the question again is, do you see this square changing the color? Maybe some of you can answer.
I see.
You do see it? Yeah, I also see it. And as you might presume, because it's called optical illusions, the color of the square is not changing. The pixel colors are actually the same. It's only that we see it different because it gets put in 2 different backgrounds. So you might not understand this now. I'll go with the next optical illusion. One moment. Okay, so the question here is this image color or grayscale? And if you guys can answer, let me check. Oops. Yeah, so maybe it was not so easy to check. Oh, one moment. In this view, it gives it, it's quite tight. So if you see it from a quick distance, you might say, oh, you know, the image is color, but actually, indeed, the image is grayscale. Here is more apparent. They did the different, you know, effects, one with the lines and one with the letters. And just by putting the colors on the lines or the letters, your brain makes the whole assembly of the image as if it were close to a color image, but it's actually just the lines or letters that are put up here. So this also happens not just with color, it also happens with such text. Here your brain is making, you know, the words are in complete disorder, but your brain is making a final composition where you can actually read the text, even though it's in disorder. So this is just to say color is an inference we make. So brain is filling in a lot of gaps to give you quick answers, all right? So we take cues on surrounding colors. I also put here the famous dress. I don't know if you ever saw it white or gold or blue or black. And if you know, I of course did the exercise, but until now I find a possible answer for this. So actually, the people, one of the study, what it says, it's not completely proved, it's one of the theories, is that people see it differently based on their more life experience. So if people are early birds, rising up early and being most of their day in daylight, when exposed to an image in dim light, the brain takes this life experience and you know, assumes that it's exposed in more daylight colors, so white and gold. But if you are a night owl, you spend most of your time in dim lights, in, you know, artificial lighting, your brain gets this life experience and you actually see it blue and black. So this is again just to prove this color is an inference we make. And you know, it's not, I don't want to say completely don't trust your eyes, but it's just to make you think, right? And why we might be inclined to using other toolings, other technologies, other methods as support to our eyes. That's the main point I'm trying to prove. So in this case, other toolings, other methodologies comes remote sensing. So here you can see a satellite image of a place. We call this a true color composite. It's close to what we see in reality. And here the bands are put in this order, red, green, blue, let's say. But when we actually switch the positions, when instead of, we're in the red position, we put the near infrared. Instead of the green, we put the red. Instead of the blue, we put the green. We get a false color composite where the colors change. And you actually see this red and cyan colors, where red means more vegetation and cyan means cities. So it's actually, yeah, here I'm just talking about the bands. These are the numbers in the bands near, so in the two satellites, red, green, and near infrared. This is in Landsat. This is just for you to be mindful. Not all the bands have the same naming format or numbering format, so just be aware of that. But most of them have the same bands. But yeah, what I'm trying to say here is that if you vary these colorations, it can be easier for your eyes, for you to detect that this area is clearly city, whereas here you might have thought that it could be desert. So this is part of these analytics that we can do, and this is made so that we can differentiate between different land cover types. So indeed, we can use algorithms that help us land use classify these different land covers, so that we detect that the red is indeed vegetation and the city is indeed indeed cyan. Another part of this analytics is using simple band equations. And one really popular one you will come across is the vegetation index. This we use it we obtaining by putting the near infrared band minus the red band divided by the near infrared plus the red band. And the output that you get by doing this, this algebra, let's say this operation, would give you an output such as this one that tells you within this agricultural field which are the parts that are most healthy. Okay, so in this case, the higher green, the darker green is the most healthy part of the field. So again, if you would be looking at this with the naked eye, you perhaps could just see plant is equal to plant. But if you see the different ranges of the electromagnetic spectrum plus using equations and analytics such as this, you would easily detect that these crops are the most healthy. I do want to say, even though by one side it might be looking that I'm saying, yes, let's go to remote sensing and satellite data for everything, it happens that, yes, this is without its constraints and limitations. Satellite data, as we said, often has clouds, especially in tropical areas, and with clouds, there are few things you can do. Just the scene is blocked. And there's also sensor gaps that, like it's due to the mechanics of where the satellite is passing. So there's also limitations to this. It's not an answer to everything, but it can help as a complement to your eyes, and just to not manually have to draw everything, but just use algorithms and equations to help you find information on the data that you have. So this is it for the theory. Now I give it to Federico to go to the exercise. And the exercise, I put the screen here, Fede. You can take over. I guess perhaps are there any questions on the theory part? I'll check the chat. Yeah, the dress.
Yes, there is a question from Andy.
Yeah, corrupted or missing data. Yeah, it is. In one of the satellites, Landsat 7, several months after they put it up, all the pictures that come out of that satellite have some lines, similar to the optical image that I put. They just have some lines that you can't get away with it. They do some, they try to mosaic it into a better view, but still, it's with these sensor affectations that you can't get away with. Yeah, if a sensor stops, also that's it. You don't have access to that. So data quality is definitely something to consider. There can be tricks. There are cloud masking operations, but it will not get you by with a huge cloud. So there are some things that people can do, and often, as Federico is saying, these are open communities, so people generally share a lot of knowledge, especially on, for example, Sentinel-2 is with the ESA, so the European Space Agency, and as such, information is quite open. But yeah, there's many steps and ways to work around for the data quality. And yeah, Parvati is saying that it's very heavy. How is it stored and processed in most of the use cases? So yeah, this is maybe Fede, do you want to share a little bit of your experience with Space4Good on
yeah,
this?
yeah, I have to say that obviously the data storage is it can be huge, specifically if you go down on the resolution. So higher resolution data means bigger data and heavier, and even computational power is needed. So it's a big issue in general, but I have to say that now it's tackled through the cloud computing data. So virtual machines that helps you to deal with data. You pay a service, and then you can store your data somewhere else, so it's not on your local. And different services now that are available as well allowed you to do even the operational part on cloud. So obviously, if this field, if we are even today here now to talk about you and say that this is accessible now, is even because of open up of the data. So the data became somehow open source, or even more open source than they used to be. And because the operational system and all the cloud computing power is getting huge, so we can access even as a, not even as a company, but just as individuals that we are just interested to do something to work with. And programs of ESA, the European Space Agencies, as Copernicus, that basically has this name just because he wants to a little bit represent this revolution on the system, on making satellite data available. And after this program, everything and everyone started to think about how this could be done and implemented for normal people that doesn't, or normal companies that doesn't have to be a big space agency institution or just a university that has the capability to work with that. So it's more obviously accessible, and it's going through that direction. So there is much more interested in such topics.
All right, so Fede, I'll stop my screen share and you can take over for the
Yes,
exercise.
I can share mine. I hope you all set with the QGIS. Thank you, Elke, for this introduction, which is basically really important as well to start with our exercise too. For who join us now, we ask you to download QGIS. It's an open source platform, allowed us to make some calculations. Obviously, the degree of complexity is basically basic right now because we want to introduce. But as I was having a private chat with someone else in here, I was saying, like, yeah, obviously there are other applications like deep learning and more complex ones that can be achieved as well, or yeah, exploited. If you already open your QGIS desktop new project, we can create a new empty project. And this time we will work not with vector data as we did before, but with raster data. So we can open the folder that you downloaded and unzipped, and we have 3 subfolders, and we have a subfolder which is called rasters. From this folder, we can drag and drop our file S2 February 2019, which is an image from Sentinel-2, so the one of the satellite we were talking about. It's an open source image. It's an optical image, so a passive system. Basically, the sun, as well said by Elke, reach out the surface, and then this backscatter is registered by the sensor, by our satellite, Sentinel-2. As you can see, once you open this, it seems like the colors are really a little bit off. We don't really realize what is there. This is because the Sentinel-2 has many bands, as said by Elke, and we want to set the right combination of bands to allow us to better visualize the image. Before doing so, we can check a little bit the resolution. We say that this is a raster. So because it's a raster, if we try to open an attribute table as we did before, this is basically impossible. But we can zoom in, go into a specific pixel. So this is a kind of the pixel level. We know that beyond this unity, there's nothing else. And we can even measure. So to check it out, the resolution of our data. And we can do it manually, for example. So with the ruler over here, let's check this. And it's, yes, it's 10 meters. So as well said by Elka before, the Sentinel-2 data have 10-meter resolution. Okay, let's change the visualization. We can double click on the layer, send S2 Feb 2019, double click, and you will have this window here where we can adjust the combination of layers. I have to put it a little bit smaller. Yes. Let's go to symbology. And as you can see, we have the 3 channels, the 3 RGB channels, so red band, green band, and blue bands. And we want to obviously, at least for now, at the beginning, use a combination of bands that allowed us to have a natural color. So all the RGB bands correspond to their actual channels. As said before, B1 doesn't mean that there is red band and B2 green band. For each specific data, we have different order of the bands. And as showed by Elka before, for Sentinel-2, we have the red band in B4, so in band 4, the green band in B3, and the blue band in band 2. So basically what we need is to set in these specific channels, B4, B3, and B2, to have a natural color composite. We can apply this 3 combination of band, and as you can see now, it's a natural color image. We can see the blue of the sea and the green of the fields. Probably I can't really see the quality of the fields yet, but it's something more clear, more clear, and obviously more something that we are more used to, at least as a user of Google Maps, for example, right? So Google Maps has a resolution of 30 centimeter resolution, 30 centimeters. So it's obviously different what we can see there. But the limitation of using such a Google images for now is the fact that they are collected, at least for that scope, just once per year and cleaned. We have instead such an image each 6 days. We can do change detection, but we have to deal as well with cloud cover, for example, or problems in the atmospheric. So we have to apply some atmospheric correction. But what can we do is change for example, the band composition. Again, double click. If we want to have a false color to announce agriculture, for example, we can change the red band. In the red band, we can put the band 11. In the green band, the infrared band, so band 8. And in blue bands, we can have band 2, which is already there. We can apply this composition, and we can suddenly see obviously other problems for sure, like this is aerosol or a problem on the atmospheric correction that we're supposed to apply. But this is a more clear image, at least for our eyes, to understand. For example, these are fields, or these are probably because are close to the water. These are rice field. This is a location in India, by the way. Okay, let's do another trial. Let's use infrareds to announce vegetation in general. This is, for example, to announce agriculture. But let's change bands again. Let's set the near infrared as a red band. So band 8, band 4 for the green, and B3 for the blue. These are just, we're trying out different composition of bands. And as you can see with this specific combination, which is called infrared false color, we can announce the greenness, or in red basically is vegetation, and cyan, as was said by Elka, is urban infrastructures. We haven't done any calculation so far. This was just basically change the combination of the bands to announce different things. But let's do some calculation now. Elka introduced before the NDVY. The NDVY is a really common vegetation index, and NDVY stands for normalized difference vegetation index. Why is normalized? Because we have a value that span from -1 to 1. And gives different information on the vegetation, as we will say before. The formula to retrieve this index is the near infrared minus red, subtracted by near infrared plus the red bands. How we do such an operation of raster on this image? We click on raster calculator, and what happens here is that we have the different bands, specifically 16 bands from this specific image. So each band is containing within this layer. And let's apply the formula then. So we have to
maybe it helps that
use
you put in the slide where the bands are listed, just because it's quite confusing, like the you know, the numbers. If you can just quickly remind the participants of the band numbers and their names in the presentation.
Yes, your slides. Yes.
Yeah.
This is the slide that Elke used before.
Yeah.
So we are now in Sentinel-2, and these are the span of bands. We are using the band 8 as a near infrared and the band 4 as a red.
Yeah.
So let's do it here. We can take the band 8 minus band 4, all divided by the band 8 plus the band 4. So this formula that we have here is basically the representation of the previous slides, which was displayed here as this formula over here. Okay, we can save the layer. Let's say that we want to save it here in our raster folder. Let's call it NDVY, which is the specific index that we are calculating for the February 2019. Let's save it and let's run it. Well, now this is the result, the output. We have this NDVY. As you see, the minimum value is -31402 and maximum value 0.78. So the range of values, as I said before, from -1 to 1. Values closer to -1 are values that represent bad quality of health and vegetation. Values that has that are closer to 1 represent a better vegetation. So we can change even the visualization of this. Double click, symbology. We can represent it as a single band pseudo color, for example, and apply this palette. I'm going really fast here, but this is something that you can find in the tutorial. And it's just, I'm just displaying how you could visualize basically this NDVY raster. So this is the image itself. this is the NDY, so the output of the calculation that we already found. In red, you found low values, and more blue in a higher values of NDY. What we do now is basically, we already prepare for you another NDY index for the February 2020, which we can basically just open from our folder. I call it, you will find there NDY February 2020. You can drag and drop here. And another trick could be to basically copy the same style of the previous NDY to see the differences visually. So you can just right click on this layer that we already applied this specific symbology already, and say styles, copy style. And here I can say style, paste style. So you can see the differences in the NDVY that are from 2019, and this one that is from 2020. Well, this is already a big thing because you can visually check what are the differences. If we focus, for example, on this specific field, probably it's a rice field. In 2019, there was no vegetation. In the same time, so February 2020, we have vegetation. But this is not still enough. We can make a differences between the two rasters to analyze really efficiently what are the changes that went on. So we can do another operation with raster here in the tab raster calculation, for example. And we can do the subtraction of 2020 minus 2019. So the two layers. We can save it in our folder, like for example, as a difference. Just do fast. And this is the difference between these two layers. This is just something that we can assess visually, but running an extra calculation which subtracts the two layers, we have now these resulting layers where we can see where the main change had happened. Darker pixel are specifically vegetation loss. And we can see from here, we had vegetation here in this part, and we didn't have vegetation anymore 1 year after. And the same things we can see for brighter pixel. These two fields, for example, indicate vegetation gain. So we had no vegetation at all in 2019, but 1 year after we had vegetation. I know that probably I went too fast, but due to time restraint, I think, yeah, I hope I was clear enough. But in any case, all the steps are present into the manual, into this tutorial document that we will share with you, and you have the data already, or if you don't, you just require us, and we will send you an email, and you can play a little bit around. This is to recap a little bit a short possibility, or a little possibility of things that you can do and you can play around. But obviously there is much more, and then it depends on the different tasks that you need to solve. Thank you for your attention. I will. Yeah.
Great.
We can have some questions, or I don't know. I haven't read the question, if there are any.
Yeah, I think, Fede, so due to time, we're not gonna share some last part of the slides. This is for another workshop, let's say, but we will deliver it to you, and just to browse through quickly, because you will receive it. The last part of the slides, one moment, sorry, break video was coming. Okay, yeah, was more where to find the data, like what are good websites that you can use both to visualize and download data. So we will send you this. For example, this is an overview of the different satellites, like Sentinel-2 is available since June 2015, whereas Landsat, you have information all the way since 1984. Landsat 7 was the one that was having the sensor problems that I mentioned. But yeah, these slides we'll share with you, and you can. It's just web links where you can use to. This one is a playground where Federico showed you manually how to calculate the NDVI, but in this playground you just do it with one click away. You just click it and it automatically gets converted. And maybe in relation to one question that was posed by do we use SNAP or QGIS? SNAP is really powerful for remote sensing, and already a lot of these equations, such as in this website, but SNAP is a software version and allows you more operations, more analysis capabilities. SNAP already has these equations embedded, and you can just click NDVI and it gets automatically created. You don't have to enter the equation each time like Federico did it. But we wanted to do it first because we already used QGIS, so use the same environment. But second, so that you can get the feel of how the bands work and how to manipulate them. And this other website is mainly for downloading the raw images and for downloading them in batch. As we said, in terms of software and toolings, Snap is a good option. At Space4Good, we of course use a lot of Python to handle all of this, or also alternatively Google Earth Engine. All right. So let me check for questions. We have around 2 minutes left. Awesome. We're really glad you enjoyed it, guys. If you have any feedback or anything, please tell us and just reach out. As we said, Shavan was our Indian colleague. He couldn't join today due to travel things, but he's making the email available in case you need data, geodata for India. He's more familiar with it. And yeah, I guess that this last slide that I'll put is this one here. Here are our emails. You can reach us out in case you have any further questions. All right. And where we will let you know where intermediate workshop of GIS and remote sensing can come up. I don't know if you would be interested in this, but yeah, this was just covering the basics. Of course, you know, there's higher level of analysis, and we will of course be happy to share this. Anything else by participants or by Parvati organizers?
No, for me, actually, I completely attended the session. I didn't skip anything. It was so interesting even for me because I have been working in GIS. So you mentioned that this is for beginners, but you mentioned a lot of use cases, potentials and opportunities within using GIS and remote sensing, which I found very interesting. Because sometimes we talk a lot about technology and less on the relevance of it in real applications and use cases. So you touched upon that right from the first example that you showed, which I think everybody appreciated. So if you look at the comments, you can see that everybody really enjoyed it and learned a lot. And like, I am sure if you do a intermediate session, I am definitely going to attend. So please do let me know. And it is great that you shared your details there. And I will share the presentation also with everybody so they can reach out to you if they have any questions. But thank you so much. I mean, it was so wonderful to have you with us, and it's a pleasure that you were able to join from Netherlands and do the session, and LK from Costa Rica. So it is really wonderful.
Yes, now I go for my breakfast.
Great.
It's
Thank
6
you so much
a.m.
for having us. Yeah.
Yeah, no.
Yeah,
Yeah,
thank you so much for having us. Yeah, absolutely.
and very great exercises. I enjoyed them too. The exercises, maybe a little bit, you know, especially for the remote sensing part. Um, we just browsed through it, but there's really cool things where you can, you know, depending on what's recorded on the pixels, what the pixel value stores, you can plot such recordings, and then even identify the different materials that exist. You know, so you can use you know, really cool uses of remote sensing in GIS. Yeah, one of the coolest studies that I have done was indeed with an advanced suitability map. So we could elaborate on these. This is more for next session, but yeah, for now, just explore what you have, explore the README, and you know, like me and Fede, we also don't have the answers. It's a lot of Googling and a lot of, you know, like, what tool do we use to solve this? There's so many ways to tackle one same problem. And that's so refreshing that you could have so many pathways to do one same analysis. So, and of course that it's visual. You always have lots of fun. So yeah, everyone, thanks a lot and have a great evening. And hopefully we see you in some time in the future.
I would like to quickly mention one thing, Elke.
Great.
Like on the 28th of November, we have our hackathon, and it is about climate resilient food security in India, which is actually having a lot of relevance to a lot of tools and techniques that you showed today, because we will be providing the participants with some remote sensing data, GIS data as well. So I'm sure that a lot of the participants from the hackathon is also part of it, and for them it will be very, very useful. So thanks again on behalf of them.
Cool, thank you. And final remark, don't trust your eyes. No, I'm just kidding. But it was quite interesting to learn about that too, for this purpose. Okay, everyone, so have a great one, and hopefully, yeah, see you in the conference, hackathon, bootcamps, masterclass, everything. And yeah, go in the data week.
Thank you. Bye.
All right, bye-bye.
Bye-bye. Bye-bye-bye.
Hi, thank you very much. It was great.